Hello my friends, welcome to this new practical activity on our second classification model, which is of course the k-nearest neighbors. We just tackled the logistic regression model and we actually made a classification template which will allow us to finish this KNN implementation in a flashlight because we will only have one cell to change. So it's really important to understand that the previous work we did on logistic regression will actually serve as a template, a classification template for the other classification models here. So I'm going to show you this in actually one single tutorial. We will be extremely efficient. And before we start, let's of course make sure we're all on the same page. So right before this tutorial, I gave you the link to this folder which contains all the codes and datasets, so make sure to connect to that link. And now we should all be on the same page, and therefore, my friends, we're going to go into part 3, classification, and then k-nearest neighbors, KNN. All right, and as usual, we're going to start with Python, and inside this folder, you will indeed find two files. Of course, the k-nearest neighbors implementation in IPYNB format, which you can open with either Jupyter Notebook or Google Colab, and the same dataset, social network ads, containing 400 observations, where each observations, each row corresponds to customers, and for each of these customers we get the age, that's the first feature, the estimated salary, that's the second feature, and their purchase decision, whether or not they bought, yes or no, the SUV. And that's of course the dependent variable. And our exercise here is to learn some correlations between these features, the age and the estimated salary, to predict this dependent variable purchased. And the goal of all this is to of course predict which customers are going to buy the new SUV so that we can optimize our targeting. All right, so exactly the same. And now we're going to open this implementation, k-nearest neighbor, with either Google Collaboratory or Jupyter Notebook. Choose your favorite. And now it is opening the notebook, laying it out in a second. So loading it, laying it out, there we go. And that's the notebook. And as you probably noticed, I actually kept the logistic regression implementation to show you indeed that all the code cells inside these two implementations are the same, all the code cells are the same except the one where we indeed build and train the model on the training set, right? So up to here, all this is the same, all this is the same. And once we reach that step where we train the classification model on the training set, well, that's where we have this single change. And then all the rest is the same. Then we predict a new result, with the same name for the classifier, which we called classifier. Then we predict the tested results here. Once again, we have nothing to change. It's all the same, right? All the same. So if by any chance you are starting with KNN, before logistic regression, I really encourage you to do logistic regression first because all these cells are explained in detail. And for this KNN implementation, we will just re-implement, that cell to train the KNN model on the training set. All right, so that's why it is a classification template which you can use to build any other classification models. And together, we will of course use this classification template to build all our other classification models, including KNN, support vector machine, kernel SVM, naive Bayes, decision tree classification, and random forest classification. And we will all build them in maximum efficiency. All right, so let's start with KNN. As you understood, the only cell that we have to change here is this one. So actually, since we cannot do it here, re-implement it here because this is in read-only mode, well, we'll have to create a new file, a copy of this file by clicking here, this button, save a copy in Drive. This will create a copy, and inside which we will be able to re-implement that cell to build and train the KNN model. All right, so let's do this. We just need to scroll down here. All the rest is the same, and there we go. So what we're going to do is just remove that cell, and there we go. Now we can re-implement that cell. So let's create a new code cell. And now I would like you to please press pause on this video to indeed try to do it yourself first. Because once again, I not only want to train you on machine learning, but also I want to train you on how to be independent and create things on your own, create your machine learning models on your own. I already guided you on how to navigate the scikit-learn API to find some information and some tools. And now I would like you to do this same exercise again. Please press pause on the video and navigate the scikit-learn API to find the class that allows indeed to build the KNN model. And then you know how to train it on the training set. All right, so in 2 seconds now, we're going to start the solution together. Here we go. All right, so let's suppose, I'm just like you. I'm not an expert in machine learning, and I would like to build and train a KNN model on the training set. So, since I actually have no idea of what is the name of the class that does it, well, I'm going to go, of course, to search it online, and inside, well, we will do it this way, scikit-learn. Then we're going to go to the first link, all right? We will end up in the scikit-learn welcoming page. Then we're going to go, remember, to API, which contains all the modules and functions and classes of scikit-learn. And now, there we go. We are looking for the class that allows to build the KNN model. So let's scroll down a bit, and if we have, too much difficulty to find it, well, we will do a Control or Command F to find it. There are many tricks, and actually you can also directly type in your search bar k-nearest neighbor class scikit-learn or scikit-learn k-nearest neighbor class, something like that. But I like to navigate the scikit-learn API because it is really well made. And so here, by scrolling down, do we find it? Yes, here it is. Nearest neighbors. So it was actually hard to miss. But indeed, we had to scroll down a bit. But that's okay, because it's really good to get familiar with the scikit-learn library. All right, so that was the name of the module you had to find. And now the next question is, which of these classes, because you see these are all the classes of this neighbors module. That's actually the name of the module by scikit-learn, neighbors. And these are all the classes that allow you to build machine learning tools, in this nearest neighbors branch of machine learning. All right, so of course the one we're interested in is this one, k-neighbors classifier. There you go, congratulations if you found it. So let's click it and let's see the whole documentation. So feel free to read it if you want. You can see what are all the parameters and also attributes. But what we actually simply need is this, the whole name of the class and the module and the library scikit-learn, because the only thing that we need really to build and train this KNN model is the name of this class to, create the object, and also the parameters here. We need to know which parameters we have to enter here in order to build a relevant KNN model. All right? So first, let's take this and let's go back to our implementation to here, paste it, and then adapt it by, doing this from scikit-learn, and then from the neighbors module of scikit-learn, we will import this class, the k-neighbors classifier. That's the class. And then, the next natural step, it is to create an object of this class, which will represent exactly the KNN model itself, the classifier. And that's why we call it classifier. And then, to create an object of this class, well, we just need to call the class again. So I'm copying this, pasting it here, and then adding some parentheses. All right, so that's the first information we need to get from the scikit-learn API. But then the second thing we need to check also are the parameters here. And you have all the descriptions here. So for example, the first one, n neighbors equals 5. N neighbors is of course the number of neighbors of your KNN model. You remember the intuition lectures, you have the neighbors that you use to make your predictions. And we have to choose a number of neighbors. And well, we can just try this value, 5. I actually know that we will get good results with this, but in your future machine learning projects, if you're using a KNN model, well, I recommend to tune it with several values. But 5 is usually good, so let's do this. First parameter, n neighbors equals 5. Good. Then next parameter, let's see. Weight equals uniform. So uniform is the default value of weight, and weight is the weight function used in prediction. And well, here we will actually keep the default value, uniform, which means that all the points in each neighborhood are weighted equally. Okay, so they have the same importance. So we will keep that, that's fine. Then algorithm equals auto, what does that mean? Well, that's basically the algorithm used to compute the nearest neighbors, and auto is the best value to choose because it will decide automatically the most appropriate algorithm based on the values passed to the fit method, the method that trains your model on the training set. So definitely here it will be simple if we choose auto. And then you have some other parameters, leaf size, of which we'll keep the default value, and P, which is the power parameter for the Minkowski metric. So there we go, that's important. That's the other parameters we will enter. The last two parameters I actually want to enter are this one, metric equals Minkowski, and P. Because indeed, metric is actually the distance you want to use to compute, the distance between your observation points and the neighbors. And we actually want to choose the Euclidean distance, which is, the classic distance equal to the square root of the sum of the square differences between the coordinates. And in order to take that classic Euclidean distance, well, we have to choose a Minkowski metric with P equals 2. So basically, we're keeping all the default values of this K-neighbors classifier class, but in order to make sure that we are using them and just to highlight them, well, let's just write these parameters with their default values anyway, because it's important to see what we're dealing with, what version of KNN we're dealing with. Okay, so let's do this quickly. Metric equals Minkowski, and then P equals 2. Perfect. And so now we have basically a classic k-nearest neighbors model with 5 neighbors and the classic Euclidean distance. Okay? And now you perfectly know how to finish this. The last step here is of course to train our classifier, which indeed we built so far but is not trained yet on the training set. So that's exactly what we need to do as a final step. And so there you go, we call our classifier, from which we're going to call our fit method, which as usual takes as input first the matrix of features xtrain, and second the dependent variable vector ytrain of the training set, of course. All right, perfect. And that's it. We are done with this implementation. All the rest is the same. We don't have to change anything else here, because indeed, since we called our KNN model classifier, well, here, to make the predictions, we already have the right name of the variable, classifier. And then same here to predict the test set results, classifier. And then same for the confusion matrix, ytest, ypred, which result from our same classifier. And then same for the visualization of the results. Sorry, I just showed them to you. I hope you didn't see, but we're going to get to that in a second. But there you go. That's the same. Same names of the variable, classifier, xtrain, ytrain. So all the rest is the same. And that's why I like to call it a good code template. All right, so now, my friends, we're going to rerun all this, right? Because we're basically done. And so to run all this again, we're going to first upload the dataset because it is not yet uploaded in the notebook. So right now, the notebook is connecting to a runtime to enable file browsing. And in a second, we should see the upload button. Perfect. So upload. And then make sure to find your whole machine learning AZ folder containing all the codes and datasets. Mine is on my desktop. So then we're going to go inside, then we're going to go to part 3, classification, and then k-nearest neighbors, KNN, and then Python, and then we select our social network ads dataset. Click open. Now it's going to be uploaded on the notebook. Perfect. And there we go. Now we can run everything. And to do this, well, we're going to click runtime here and then simply run all. And let's just start from here. Okay, great. Our k-nearest neighbors classifier was created and trained properly. And at the end, so all the predictions are generated again. We can actually have a look at them. And wow, we seem to have some great predictions. That's, remember, on the test set. So all this is correct. Here we have an incorrect prediction, meaning that the KNN predicted this particular customer to buy the SUV, whereas in reality that customer didn't buy the SUV. Then all this is correct, all correct, all correct. It seems really good. It seems to be some great predictions here. Here we have another incorrect prediction, this time the opposite one. Our model predicted that this particular customer didn't buy the SUV, whereas in reality that customer bought the SUV. All right, correct, all correct, all correct. So pretty good. Wow, I think we actually have very, very few incorrect predictions. Let's actually check it out right now. Okay, no, so I didn't see it properly, but we actually have in total 4 + 3 incorrect predictions. That's really, really good. That's better than the logistic regression model. Remember, we had actually an accuracy of the test set of 89%. So here clearly the k-nearest neighbors did better than the logistic regression model, and you will perfectly understand why when I show you the visualization. So it's actually here. All right, so 4 plus 3 equals 7 incorrect predictions, then 64 correct predictions of the class 0, meaning 64 correct predictions that the customer doesn't buy the SUV, and 29 correct predictions of the class 1, meaning 29 correct predictions that the customer buys the SUV. And then we have indeed 4 incorrect predictions of the class 1, meaning 4 incorrect predictions that the customer buys the SUV, and 3 incorrect predictions of the class 0, meaning 3 incorrect predictions that the customer doesn't buy the SUV. So very, very good. And now, as you can see, it is still executing the cell that plots that 2D array, showing all the prediction regions and prediction boundary of the KNN model, first on the training set and then on the test set. And the reason why it is taking some time here to execute, oh, there you go, we are about to have it in a second, yes. So perfect timing. But I was going to say, the reason why it takes some time to execute is simply because, the KNN model is actually very compute intensive. There are a lot of computations when running the KNN model, and that's why it took some time. And so now let's interpret the results. So remember, with the logistic regression classifier, the prediction boundary was a straight line, and that's because the logistic regression model is a linear classifier. We will actually see another type of linear classifier in this part. But remember, for linear classifiers, the prediction boundary or prediction curve for classification is a straight line. And in 3 dimensions, it's a straight plan, and in n dimension, it's a straight hyperplane. And so here we had a straight line, which therefore resulted in having a lot of incorrect predictions, because as we can see, there are a lot of green points here, green customers who bought the SUV in reality that fall in the red region, where we predict indeed that the customers don't buy the SUV. And same for these ones here, here we have a lot of customers who in reality bought the SUV, but were predicted not to because they fall in the red region. And so what we were hoping for is to build a new classifier for which the decision boundary, separating the 2 prediction regions, does something like this, would not be a straight line, but some kind of a curve catching all the red points here without catching those green points here and here. Okay, so that's what we were hoping for, and well, that's exactly what we got here. Thanks to our KNN model, we don't get a smooth curve, but we get actually some kind of a curve that indeed catches all the red points here without catching the green points and leaving those green points and these ones inside the green region, where they should end up, right? And of course, here we have some green points that were super hard to catch because they are stuck in the middle of all those red points here, so that's fine. And anyway, in machine learning, we want to avoid overfitting, when we have some too perfect predictions on the training set, and therefore probably resulting in having bad performance, bad predictions on the test set. And well, speaking of the test set, let's see how our KNN did. It should be fine now, yes, it is executed. And once again, we get excellent results, right? Because same, the KNN prediction curve or prediction boundary or even decision boundary catches all the right customers, the red customers who didn't buy in reality the SUV, therefore leaving the green customers who bought in reality the SUV in the right prediction region, the green region. Okay, and of course, we still have some wrong predictions, incorrect predictions, but that's because the training was properly run, without overfitting, and that's why here we can clearly see our incorrect predictions. These 2 customers here and this one who are indeed the incorrect predictions that the customers bought the SUV, whereas in reality they didn't, because these are red points falling in the green region, and the other incorrect predictions here, which are incorrect because these are green customers, therefore, who in reality bought the SUV, but were predicted not to because they fall in the red region. Alright, so that's already much better. We get much better results for indeed this particular data set for which, well, nonlinear classifiers that can have that kind of curve is a better fit. And indeed, we increased the accuracy of the test set by 4%. And now the question is, can we do even better than this, with our future classification models? Well, that's exactly what we're going to find out in the next sections when building our future classification models, which include SVM, kernel SVM, naive Bayes, decision tree classification, and random forest classification. Take a bet on what is going to bring in the end the best accuracy. And well, my friends, follow me in the next practical activities to discover the big winner. And until then, enjoy machine learning.